Welcome to lesson 2.2 on density curves. The question is, what is a density curve, and when would we use a density curve, and why? A density curve is two pertaining characteristics. One is that they're always on or above the horizontal axis, the x-axis. Two is that it has an area of exactly one underneath it. Create a density curve to smooth out a histogram so you can more easily make predictions about the areas under the curve. A density curve is easier to use than estimating bar heights or counting lots of dots on a dot plot. Use a density curve so you can more easily describe the overall pattern of the distribution. How can you identify the mean and median of a density curve? Okay, the median is the equal areas point. This is the point that divides the area under the curve in half. So if you have if you had a histogram, you'd look for the place where half the bins are to the left and half are to the right. But in this case, we kind of treat it like half the area is to the left and half is to the right. The mean is instead the balancing point if you made the density curve out of metal, like a metal wire, and then you tried to balance it on your finger. This is where the metal, think a pipe cleaner maybe, would balance. So next, the Deutsche Mark has the normal curve on it to commemorate the work of Mr. Gauss. Okay. All right. So, according to the CDC, the heights of 12-year-old males are approximately normally distributed with a mean of 149 centimeters and a standard deviation of 9 centimeters. Sketch this distribution, labeling the mean and points 1, 2, and 3 standard deviations from the mean. So we draw a number line with seven evenly spaced out tick marks. Label the one in the middle with the mean value, and those on either side plus or minus a standard deviation or 2 standard deviations from the mean, and so on. So we start with a tick mark in the middle for 149 centimeter male, and then we count up 9 centimeters and down 9 centimeters for all these tick marks. Okay, and then after that, we can put a label. Then if you put a dot, which will represent the max above 149, then you should go left and right of it and put dots above 140 and 158, 1 standard deviation away, and they should be about 60% as high as the max dot here. And then if you go 2 standard deviations away, that should be about 15% of the height of the whole curve. So it should be about 15% high. And then over here, these should be just above the line. Okay, and this represents a density curve. Instead of having many, many bars, we can just have a smooth curve, and that represents 100% of males' heights. Standard deviation at the inflection points. Okay, so standard deviation is kind of right where it starts changing from concave to convex. So standard deviation occurs right kind of in the middle of the flat part here. Okay. Okay. Normal curves are really just traces of dot plots. They always mentally fill a normal curve with dots so that you understand that normal curve is filled with individuals. For each of the approximately normal distributions below, calculate the percentage of values within 1 standard deviation of the mean, within 2 standard deviations of the mean, within 3 standard deviations of the mean. So here's a dot plot showing the weights in grams of 36 Oreo cookies. The mean of this distribution is 11.392. I kind of marked it off with a dotted line, and the standard deviation is 0.081. Then I counted up 1, 2, and 3 standard deviations below and above, and I started to mark off barriers just to show you where those cutoffs would be on the number line. And then I said the mean is with mean plus or minus 1 standard deviation is anywhere from 11.311 to 11.473, and then there are 26 out of the 36 dots within 1 standard deviation, so that's 72% of the Oreo cookies. Weights are within 1 standard deviation, and from 11.230 to 11.554, I'm within 2 standard deviations of the mean, and I had 34 of the 36 dots within that interval, so therefore there are 34 of the 36 cookies with weights in that interval, and so that's 94% of the cookies. And then the last interval had 100% of the cookies in that interval. Here's a dot plot showing the scores for 50 students in an algebra test. The mean of this distribution is 76.4, and the standard deviation is 7.9. So what I did here is I marked off plus or minus 1 standard deviation, 2, and 3, and I found these values here, that there are 33 out of 50 students within 1 standard deviation, 48 and 50 within 2 and 3 standard deviations. So let's just compare these findings. The final findings here were that there was 72% of Oreos within 1 standard deviation, 94% of Oreos within 2, and 100% of Oreos within 3 standard deviations. For the student scores, there was 66, 96, and 100. Do we see some similarities? 66 and 72 are somewhat similar. Those are 6% away. 94 and 96 are pretty similar, and 100 and 100 are pretty similar. What do you think are we going to notice here? These are small samples. These are 50 students. These are 36 Oreo cookies. Let's try it again. Here's a dot plot of Tim Lincusum, strikeout totals for each of the 32 games he pitched in during the 2009 regular season. The mean of this distribution is 8.2 with a standard deviation of 2.8. So we count and we board it off, and we get all these relationships here. 72% of games are within 1 standard deviation, 94% of games and 100% of games are within 2 and 3 standard deviations of the mean number of games, strikeouts he had per game. All 3 of the distributions above were approximately normal in shape. Based on these examples, about what % of observations would you expect to find within 1 standard deviation of the mean of a normal distribution? We'd expect to find about 68% of the observations within 1 standard deviation of the mean. Within 2 standard deviations, about 95, and about 99.7% of the data within 3 standard deviations of the mean if the data is distributed normally. So what is the 68, 95, 99.7 rule? What is it also known as, and when does it apply? It means that 68% of data falls within 1 standard deviation of the mean, 95% of data falls within 2 standard deviations of the mean, and 99.7% of data falls within 3 standard deviations of the mean. It is known as the empirical rule. It applies only to normal density curves, or normal distributions. Do you need to know about Chebyshev's inequality? No, this is not an AP topic. It is a rule that applies to areas under the density curve that fits any shape distribution, so non-normal ones. It's used for area of skewed distributions. It's described on page 112. Okay, in the meantime, let's get back to the empirical rule, which is 68, 95, 99.7, which means that 68% of data was within 1 standard deviation, and so on. Okay, so what that means is about here. Using the earlier example, about what percentage of 12-year-old boys would be over 158 centimeters tall? So now we have these generalizations. If I had a measurement on the x-axis that I was curious about an area that it cut off, and it was exactly on 1 or 2 or 3 standard deviations from the mean, like 158 inches, then 158 centimeters, then we can use the empirical rule that says that 68% of data is within 1 standard deviation, 95% of data is within 2 standard deviations, and 99.7% of data is within 3 standard deviations, and we can try to make subtractions here. So if I know that that's 50% of data right there, then I know that I don't have any boys' heights that I'm curious about in that interval. Over here is another 50%, and especially right here is half of 68%, so 34%. So if I said that this is half, take away 34, I could find the remaining amount. So, okay. Or I took 1 minus 0.68, which is the whole middle, and then I got left and right left over. Then I divided that by 2 because I only have right that I'm curious about. Okay, so about 16% of boys have heights taller than 158 centimeters tall. Be careful that 99.7 is not the whole, so be careful that you don't try to take away parts from 99.7, okay? Otherwise you'll be off by just that 0.3. About what percentage of 12-year-old boys will be between 131 and 140 centimeters tall? First thing we should do is plot it out to make the tick marks, figure out where 131 and 140 is. We should plot at least those and the mean, okay? And then we should work out how to subtract for that area. It looks like we took the 2 standard deviation, so the whole middle area, out -2 and +2 standard deviations away. And then we took out the white area, and then we divided that by 2. So 0.95 minus 0.68 divided by 2 is 0.135. About 13.5% of 12-year-old boys' heights are between 131 and 140 centimeters. Suppose that a distribution of test scores is approximately normal, and the middle 95% of scores is between 72 and 84. What are the mean and standard deviation of this distribution? 72 plus 84 divided by 2 is 78. So 78 is the mean of this distribution. The standard deviation is 84 minus 78 divided by 2, which equals 3. Can you calculate the percent of scores that are above 80? No, we can't. Not yet. We only know the empirical rule, which only works with values on the x-axis that are explicitly 1, 2, 3 standard deviations away from the mean or on the mean, okay, and intervals within that. Thank you.